Go. And we're live. Yes, we're back. Wonderful yet again. I don't even know. I feel like this week's kind of going on forever, but that's just me. Okay, so as I'm kind of stalling to allow people to get into the live chat, I'll remind those in the live chat to please leave their comments right there. That'd be fantastic if they would. Kind of allowing people more time to get in. But here's my plan for today. Number one, I want to revisit the problem that we worked on for the majority of class on Monday. I want to revisit that problem and kind of deep dive it a little bit farther in terms of the mechanics that happen within the problem. After that, my main goal for today is another smaller version of it, but multiple choice challenge. Now, this multiple choice challenge, again, I'm trying to figure out various ways of being able to throw multiple good AP level multiple choice questions at you. But a lot of websites don't already have them pre-programmed. So I do have something kind of set up on quizzes, which I'm going to explain when we actually get there. But I do have that multiple choice challenge for you. At some point, you will need your Chromebooks, not exactly at this moment. But we will get there. So there we go. There are some people doing that. Oh, he's supposed to be here. Sorry, just kind of pointing things out. Anyway, so if you would, ladies and gentlemen, if you do not already have them out, I'm going to need those notebooks out and open. Okay. Flip that around. There we go. Okay. Now, like I said, I just want to revisit the problem that we did on Monday. Simply because there is a bit more to discuss than what we have originally done. So this is 2 prop test interval continued. And today is the 10th. All right. Last class, we talked about 2 samples of babies, and they were specifically looking for whether or not these babies had low birth weight. The 2 samples in question, just for the sake of argument, P sub 1 hat, and I want to specify that that's a hat, 0.08 or 8% had low birth weight. And we've written down this information before, but I'm just writing it down shorthand so that we can build upon it. With a sample size of 182. That was the proportion of babies who were born near and around the 9/11 site after it happened, who ended up having low birth weight, possibly as a result of their mothers inhaling ash, smoke, debris, things of that nature. Then there was the other random sample, and notice I'm distinguishing them with little subscripts. So on the left side, I put P sub 1 hat, and on the left side, I put N sub 1 hat. That's N sub 1. There's no hat on that N, whatever. But on the other side for the P sub 2, it was 0.044%, but the sample size was obviously a bit larger at 2,300. Now, we ran on the calculator, really. I believe we just ran it on the calculator. Just going to double check because we did there it is. Yep, 2 prop Z test on the calculator. And we got a p-value of 0.0033. So we ran a 2 prop Z test and got a p-value of, and I already forgot the number, it was 0.0, come on you. Why can't the page turn? 0.0033, there it is. Now, based on the test that we made, based on the test that we put together using the null hypotheses and whatnot, was based on this p-value being low enough, we were able to reject the null hypothesis. In general, a null hypothesis is there's nothing going on, there's no difference, there's nothing out of the ordinary. That's what a null hypothesis generally is. And a lot of the time you have to express that using, well, the notation that we just did, for example, the other day, where we did p sub 1 minus p sub 2 equals 0 for the null, meaning no difference. We rejected it, meaning that we had evidence to suggest that there was a difference. More specifically, the alternate hypothesis being greater than 0 when you subtract those numbers. We actually had evidence to suggest that babies born near the 9/11 site had a higher chance or were more likely to have low birth weight. Okay. Now, the whole point of this is that we ran the test on the calculator. I want to take a little bit of time right now and actually run that same exact test, but I want to run it using normal CDF because you have that option. You technically have that option. And this is the most important part, the mechanics behind putting that normal CDF together may benefit you in the future with certain multiple choice questions. We got to build up our knowledge base of this. So, ultimately, let me put this on the next page. We had a null of p sub 1 minus p sub 2 equals 0, and an alternate of p sub 1 minus p sub 2 is greater than 0. P sub 1 being near 9/11 site, and p sub 2 being not near. That's just stuff I want to put to the side for myself. We are assuming that there is no difference between the two. Currently, and it's on my other page, but I'm going to ask you guys, what is the difference between the samples? What is the difference between, listen to that word, the samples? It's not on this page. It's on the previous page. I'll bring it back. Currently, what is the difference between the samples? Yeah. Say again? Yeah, 0.004. It's 4%. Just subtract the two. Yay! That's the difference that we found in the samples. So just for the sake of argument, again, I'm going to put 0.04 here because it was 0.08 minus 0.04. That was the difference in the samples. Remember what the definition of a p-value is. The p-value, in this case, we got 0.0033. The p-value is the probability of seeing these sampled results given that the null hypothesis is true. That is the pure definition as to what a p-value is. There's multiple ways of wording that, but when you break it down to its just core point, a p-value is the chance that you would see such sampled results given that the null hypothesis is true. Assuming that there is no difference, what are the chances that we would see such a difference in the samples? That's what they're truly saying. So, ultimately, we are going to run, and we should be getting an approximate p-value, but we are going to run a normal CDF of 0.04, comma, big number, meaning a difference of 0.04 or greater, given a mu and a sigma, given a mean and a standard deviation. Goodness gracious. What do I put for my mean? What in the heck do I put for my mean? Oh. The mechanics behind that are going to be very, very important. The assumed mean, the assumed difference between the two currently is 0. That is what we assume the difference is at the moment. So I'm going to put a big old 0 there for my mean. I'm going to put a big old 0 there for my mean. Where's my other? There it is. Cool, cool, cool. But the big issue is what we put for the standard deviation. The big deal is what we put for the standard deviation, and that is the purpose of what I'm trying to do for the first part of this class period. I mentioned it last class. Hey, the calculator could do it for you. Great. But it is important to know what that standard deviation should be. It is very important to know what that standard deviation should actually be. This is the combined standard deviation. This is, well, I'm going to have to take the difference between those standard deviations. I mean, yeah, the means, you just easily subtract them. No big deal there. Fantastic. Yay. But in terms of the standard deviation, I cannot just subtract the standard deviations and hope that that's the one thing that I type into the problem. Instead, I'm going to have to do something a bit more elaborate. So let me see what I got here. So for the time being, I'll put a little question mark there, because this is what we're going to figure out, the standard deviation that should go in that spot. So first of all, near 9/11, if we're going to calculate a form of a standard deviation, it's not exactly a standard deviation, but for the sake of argument, this is what we got. Typically in the past, we would do something like this. I already forgot. What was the sample size of 9/11? 182? Cool. And not near 9/11 site would be this calculation. Now, I could figure out what this decimal is. I know it's 2300. I know that. I could figure out exactly what those decimals are at the moment, but it would better suit me to leave them as is temporarily. It would suit me to leave it as is temporarily, because it will make it a lot cleaner when we get down to this. It'll make it a lot cleaner. So let's see what we got to do here. Now, keep in mind, the answer that we're going to get is going to be slightly different than the one that the calculator would end up doing. So please keep that in mind. There is going to be a little bit of a discrepancy, for the lack of a better term. Well, let me see how I'm going to combine these two standard deviations real quick. I'm going to combine those two standard deviations. I cannot just subtract them because I have to find the difference between them. I can't do that. Instead, as we talked about at the end of class last time, we're going to have to do this thing where we convert them to variance. We did this, I don't know how many chapters ago. But if you want to combine standard deviations, whether it be through adding or subtracting, you have to convert it to variance first. Now, this is why I'm not figuring out what the decimal is of these fractions just yet. I'm not figuring out the decimals, because if I want to convert them to variance, I would square them, and that would get rid of the square root. Now, remind me, whether you are subtracting standard deviations or adding standard deviations, do you guys remember what I wrote into your notes? about combining variances. I'm going to go back up to the board real quick to kind of write this and then erase this. It was like, I think I did something along the lines of this. I can't remember exactly what letters I used. It doesn't matter what letters I used, but it was like the idea of like, okay, well, if I wanted to combine these two variances, well, I could take the variance of x and just simply add the variance of y. No harm, no foul. Yay, I did it. And then if you did the variance of x minus y, I wrote it again like this. And do you know what I wrote there? Do you remember? You remember? Not a typo. That's not a typo. Whether you are combining the variances through adding or subtracting, you add them. Creates a larger spread, so to speak. Then, after you combine them, you square root them back to be a standard deviation. You square root them back to be a standard deviation. These skills that we have been seeing throughout the school year will, in various ways, kind of just pop up into the problem. In various ways, they will pop up into the problem. We need to be ready for them. So, for the sake of argument, I would take these two standard deviations, I would square them. Now, keep in mind, again, I'm not going to the calculator just yet, because when I square the left side, I get that. I don't care what the decimal is. And if I square the right side, I get this. Again, not caring what the decimal is. Then I would add them together. And then ultimately, I would square root them back. That's a weird square root symbol. There we go. There are formulas that they try to give you to do stuff like that. But in reality, if you remember the concept of how you combine standard deviations by converting to variance and then converting it back to standard deviation, if you remember the concept behind that, you don't have to memorize formulas. In this case, you don't. It's like, oh, I can't just add standard deviations or subtract them. I have to convert them to variance by squaring, then add them together, perform whatever I need to perform, and then square root them back. Yes, if you remember that concept, it'll apply here. I want to say, I can't remember if they actually gave it to you on the AP test. I want to double check that real quick. Let's see, AP Stat 2019. Pre-response questions. Let me see here. Oh, yeah, they kind of do that. Look at this. Hold on, I'm going to zoom in right here. Maybe that little wider screen right there. Look at that junk right there. Look at that junk right there. This is on the formula sheet for the AP test. They give you this formula right here. And it's like, oh my, like that's, you know, the first time somebody sees something like that without knowing the concept behind it, they're like, holy crap. But that's combining sample standard deviations right there. Just is. That's what it does. Well, they don't show the process behind squaring them, adding them and squaring. They just show the whole formula. It's just there. There is a special case, but that special case is incredibly rare, and I doubt you will ever use that special case formula. But they do throw it at you on this thing right here. Oh, there we go. So let me figure out what this thing is actually supposed to be here. Let's see. I'll do it a piece at a time. 0.08 times 0.92 divided by 182 plus 0.04 times 0.96 divided by 2300. I get that messed up number, but then of course I have to square root it back. There we go. This is approximately 0.0205. 0.0205. And that's the number that I'm going to throw into that normal CDF. Let's see what we get here. Normal CDF, 0.04, comma, big number, comma, 0, comma, 0.0205. A couple things to keep in mind. When we did this problem on Monday, we had to make an adjustment. We had to make an adjustment in the 2-prop z-test. I just want to zoom in real quick before we actually do that. In the 2-prop z-test, oh, I did what's 1-prop. Hold on. In the 2-prop z-test, I believe when we typed in the information, we did something like this. It was like 0.08 times 182 and 182. And then it was 0.04 times 2300 and 2300. But I can't leave the number like that. If I leave the number like that in 2-prop z-test, watch what happens. Watch what happens. Calculate. Oh no. It doesn't work. And the reason why it doesn't work is because I have to have that be a whole number. Putting that up to 15 shouldn't make too much of a difference. But it does slightly. It changes that 8% number. It does change that 8% number slightly. So we do get a certain p value. If I were to do this calculation with normal CDF, 0.04, comma, big number, comma, 0, comma, 0.0205, I'm going to get a p value that is in the ballpark, so to speak. You can kind of see it right there. It's a little bit larger. We get a p-value of 0.026. Does it change our conclusion? I'm seeing several heads shaking. No, you're correct. It does not change our conclusion. We still reject the null hypothesis because that number is less than the alpha level of 0.05. We still reject the null hypothesis. It is a slightly different number. It's slightly enlarged as a result. But like I said, it doesn't change what we got. The reason why the number is a little bit larger than the other p-value has to do with the fact that, well, for here, we put a difference of 0.04. And I believe when we did the 2-prop z-test, yeah, we had to elevate that 15. It was like 14 and change. We had to bring it to 15, which actually enlarges the difference that we had there. It's very strange. Okay. One more thing I want to show you before I get to that multiple choice thing. One more thing I want to show you because I wanted to show you the mechanics. This is the main point of this morning. I wanted to show you the mechanics behind combining the standard deviations, which we've already seen, but I wanted to show it to you one more time. There we go. 2-prop z-int. 2-prop z-int. I'm going to run this one in the calculator. You're going to see how this one works. Actually, let me bring up the other calculator. There it is. Click. Stat. Tests. Come on, tests. 2-prop z-int. It's like option B on those calculators. It's similar to what we did the other day. In fact, those numbers are still there. Those numbers are absolutely still there. For the sake of argument, I'm going to put these numbers in as I have them on the calculator. I'm just writing down this information. I'll show you what I'm writing down in a moment. And let's just say 95% confidence level. This is what I just wrote down. The point of me showing you this 2 prop z int now is so we can actually look at the interval and properly interpret what it's telling us. So those numbers are going to be typed into the calculator, as you can see right here. And I'm going to calculate that thing. The order in which you put those numbers in make a huge difference. But this is what we get. I'm going to write down 0.00167, comma, 0.08316, parentheses. Here's the interval. When you conduct a 2 proportion z interval, if you put the numbers in that order, in this case, the first sample was near 9/11, 8%, and the other one was not near 9/11, 4%. The 2 prop z interval will create an interval of the difference between the two. The 2 prop z interval is working with the assumption that we don't know what the true proportion is. Or, I'm sorry, let me rephrase, the true difference in proportions. Let me write down this statement right here. It doesn't interpret the interval, but it does help show the difference between this and the hypothesis test. This interval is attempting to capture the true difference in proportions. This interval is attempting to capture the true difference in proportions. It's taking the 0.08 and the 0.04 and subtracting them as the baseline. That is actually the center of this thing right here, believe it or not. 0.04, 4% is approximately the center of this interval. And then it's calculating a margin of error based on a z-star and based on the combined standard deviation. So it goes from 0.04, and then it adds a bunch, and then it goes from 0.04, and it subtracts a bunch in order to create the interval that you are attempting to capture the true difference in proportions. Now I'm going to make this statement. I am 95% confident that the true difference in proportions between babies born near 9/11 site and not near born 9/11 site is within this interval. I'm 95% confident that the true difference of the low birth weights is in this interval. Listen very carefully to what I'm about to say. We can use this interval as evidence against the null hypothesis. We can use this interval as evidence against the null hypothesis. Why? How do I know that? Ooh. How in the world is this interval evidence against there being no difference between birth rates of babies born near 9/11 site and not near 9/11 site? Yeah? Yeah. That's the key. That's exactly the key. 0 is what we assumed was true. We assumed there was no difference. Then we created this interval and this interval does not contain the number 0. That's exactly the evidence that we have. Now, are we guaranteed to be correct? No, we're not guaranteed to be correct. We're only 95% confident, but it is evidence against there being no difference. It doesn't contain the number 0. It's really messed up. In fact, check this out. Just one more thing before we jump to that multiple choice thing that I wanted to do with this problem itself. Actually, I'll do it on the calculator over here. Check this out. If I go down back to, there it is, 2 prop z int. Watch what I'm about to do here. I'm about to switch up these numbers. Good. I switched the numbers up. It's the same interval. It's just mirrored on the other side of 0. It's the same exact interval. It's just mirrored on the other side of 0. Same conclusion. It doesn't contain the number 0. Thus, this is evidence against there being no difference. Love this stuff. We are going to be spending a bit more time, like with hypothesis testing. The last couple of chapters that we've been working on, the last actually 2 or 3 chapters that we've been working on, have been dealing with hypothesis testing of proportions. I'm not leaving it alone just yet. I need to stay with this information for a little while. Yes, there will eventually be assessments as we roll through this thing, but hypothesis testing is one of the most important aspects of AP statistics, and we need to make sure we have this down. So with that, I have a multiple choice challenge for you. What I'm going to ask you all to do, for those of you that are in the classroom, if you don't already have your Chromebooks out, I'm going to need those Chromebooks out. I have 10 multiple choice questions for you. 10. Now, what are those questions? Look at these questions right here. Look at these wonderful questions right here. They say nothing so far. Because here's what's going to happen. The questions are going to be on a PDF that I am about to post to your Google Classroom stream. The questions are going to be on that Google Classroom stream in a moment. First, I want to make sure we get signed into the quizzes. Start a live quiz, classic. Let's see. I don't want to shuffle questions. I don't want to shuffle answers. Okay, good. Continue. Boom. Now, I'm going to actually move this over a little bit. Check this out. I'm going to move this like this. There we go. That's the code that you need to type in. Now, I believe if I did that correctly, then people in the chat should be able to see that number. Yes, they can. 797701. Go to joinmyquiz.com and join that thing up while I get the PDF into the Google Classroom. Let's see here. Again, just experimenting with this. I've had to improvise a lot in regards to how I do things with people online and in the classroom. There we go. Double checking, making sure it's the correct PDF. Okay, yes it is. Yes it is. Okay. So, multiple choice PDF. I haven't posted it yet. I have not posted it yet. I'm giving people an opportunity to get into the quizzes. Now, what I'm going to do is I'm going to post the PDF. I'm going to give you a few moments to make sure you can get it open. Then I'm going to click start on the quizzes. I did not shuffle the questions and I did not shuffle the answers. So every question should relate directly to the number that is on the PDF that you're about to see. So again, just giving people an opportunity. It's like what, 3, 4, 5, 6, 7, 8, 9, 10. I get 10. Yes. Yes, but keep in mind with quizzes, a couple things. Number one, even if the timer runs out, you still have an opportunity to answer it. But number two, I told you guys like last week or something like that, or the week before. I'm trying to train you guys to get your multiple choice times to a manageable level because you need 2 minutes 15 per question on the AP test. So it's kind of a catch-22. This doesn't count against you, and it's like 2-minute timer. Oh no, I'm gonna panic. But maybe that panic is good for the training because it doesn't count against you. Anywho, okay. I'm going to get this thing started in a little bit, but like I said, first, go to Google Classroom. Let's make sure you can see the PDF. I'm going to post it right now. So please make sure that you can see that PDF. Is that good? Okay. Now, the questions actually go up to 11, but 11's not a multiple choice question. It's not a multiple choice question. So please keep that in mind. All right. I'm going to get this thing started. So once I click start, then obviously things will begin on your quizzes. Every number that's on there, I believe I labeled with a number. So it should just say like 1, and then it should be A, B, C, D, E. There are 5 choices per question, clearly. Let's see what we do. I'm going to click start. I'm going to give you guys about one more a minute to wrap up because I want to at least go over some of these questions before the end of the class period today. Right. I'm going to end it on that. There we go. Just because I want to show it off. I want to show you off this picture. Hold on. I want to show off this picture so everyone can revel in what I revel in. Look at this. Do you see this? First of all, absolutely adorable, but I want you to know something about this. My wife sewed that entire outfit together. Be jealous. Just saying. Hold on. Just look at her face. It's like she's like, what am I looking at? That's how she poses. Anyway, back to this. And bring this over. No, duplicate. There we go. Good. Okay. Questions on here. So let's start with the red questions, and then we'll kind of backtrack a little bit. Sort by accuracy. There we go. Jump to the bottom. Boom. Question number 9. Question number 9. Now, just for the sake of argument, I do have this, but it's a little bit difficult to see this, which is why you have a PDF of this. Whether you're in class or at home, you have a PDF of this particular problem. So let's see what number 9 has to do. Number 9, suppose that a manufacturer is testing one of its machines to make sure that the machine is producing more than 97% good parts. The null hypothesis is P is equal to 0.97, meaning there's nothing going on, nothing out of the ordinary, nothing crazy. And the alternate is greater than 0.97. The test results in a p-value of 0.122. Now, before I read any farther, let me just think about the 0.122. If it's a 0.122, that p-value is not low enough. It's not low enough, meaning I would fail to reject the null hypothesis. And if I'm failing to reject the 0.97, then I'm basically saying, well, I don't have enough evidence to show that the machine is producing more than 97% good parts. Okay. Unknown to the manufacturer, the machine is actually producing 99% good parts. Oh, snap. What probably happens as a result of the testing? Okay, well, hold on. I am going to fail to reject. That is going to be my conclusion. Because of the p-value, I am going to fail to reject. But I'm failing to reject the 97%, even though the machine is producing at 99%. Oh, snap. I have made a mistake, but if I'm failing to reject the parachute, what type of error would I be making? If I'm failing to reject the parachute, what type of error am I making? Type 2, because I'm going to die. I'm going to jump out of that plane. I'm failing to reject the parachute. That's type 2. So failing to reject could be a type 2 error. Rejecting could be a type 1 error if the mistake was made. So hold on. So let's see. They correctly fail to reject. Nah. They correctly reject. They reject the null. No, I said I was failing to reject. There we go. It's either got to be D or E. I'm failing to reject and thus making a certain type of error. But if I'm failing to reject the null, I would be making a type 2 error because that's jumping out of the plane with the parachute and dying. Let me see what y'all chose for that. My marker. So for number 9, boom. A bunch of you chose C. A bunch of you chose C. Obviously, 2 of you chose E, the green one. What was C again? C was they reject the null, making a type 1 error. Now, if you rejected the null and made a mistake, then yes, that would be a type 1 error. But based on this p-value, it's too high. You would fail to reject. Remember, rejecting is if the p is lower than the alpha level. Now, they didn't mention an alpha level, which is why you assume the alpha level is 0.05. Let's see what else we got here. Going back one. No, get out of there. Get out of there. There we go. Question 8. I didn't want that first. I want to go here. Here we go. Question 8. Not wanting to risk poor sales for a new soda flavor, a company decides to run one more taste test on potential customers. This time requiring a higher approval rating than they had for earlier tests. This higher standard of proof will increase what? Okay. This time requiring a higher approval rating than they had for earlier tests. Okay. Here's my marker here. I don't know what these numbers are, but let's talk about a null. So the null hypothesis is the approval rating. Let's just say the rating stays. The null hypothesis is there's nothing going on, nothing out of the ordinary. The approval rating did not change. That's the null hypothesis. But they're looking at an alternate of the rating being higher, significantly higher than what they had for earlier tests. They want a higher standard of proof. They want a higher standard of proof so that they can reject that null hypothesis. They want to reject the null hypothesis, but if they're going to have a higher standard of proof, it's going to be a little bit more difficult to reject the null hypothesis. Meaning, a higher standard of proof is when you take that alpha level and you bring it down. If my alpha level is 0.05 and I want a higher standard of proof to be able to reject that null hypothesis, I might bring it down to 0.01. But if I bring it down to 0.01, what happens to my beta level? It goes up. Now, the beta is the chance of making a type 2 error. Now, the higher standard of proof will actually decrease my type 1 error. It will decrease my type 1 error because that's alpha. Alpha is the chance of making a type 1 error. But if I increase my standard of proof, I'm basically taking that alpha level and bringing it down, thus decreasing the chances of a type 1 error. But inversely, I'm increasing my chances of making a type 2 error. But if I increase beta by accident, not by accident, but if I increase beta, what happens to my power? What happens to the power of a test? Yeah, it goes down because 1 minus beta. Thus, bring it over here. The answer is B. A lot of you chose A, and I can see why. You were thinking standard of proof, they were raising alpha perhaps, but in reality, it is bringing alpha down. It's a higher standard of proof to be able to attempt to reject that null hypothesis. You want to reject that null hypothesis, but you want to have a higher standard, which means that alpha level is actually going down. One more. Let's see what we got here. Wait a minute. Let me go back there real quick. Do you see the average time? Just wanted to point that out. Oh, that's funny. All right, number 3. We'll wrap up with number 3. Do we have time for number 3? All right, we'll see what happens. I don't know, because I may have to do a calculation for number 3. We have calculated a confidence interval based on a sample size of 100. Now, we want to get a better estimate with a margin of error that is only 1/4 as large. If you want your margin of error to be smaller, keep in mind, margin of error, z star square root p hat q hat over n. You're not changing z star. Most likely, you're not going to be able to change or control p and q. The only thing you can really change is n in this case. That's what they're talking about, the new sample size. If you want it 1/4 as large, you're definitely going to have to increase the sample size, which means it can't be A and it can't be B. So it comes down to those 3 choices. You got a 1 in 3 chance. How large does our new sample size have to be? Well, we want it to be 1/4 as large. The margin of error, that is. We want it to be 1/4 as large. Well, let me take that 1/4, and again, I did not teach you Algebra 2. If I mention Algebra 2, do you get that tingling feeling in PTSD? Okay, I didn't teach you Algebra 2. But basically, you can take that 1/4, and you can bring it back into the square root. But the second that you bring that 1/4 back into the square root, it becomes a 16, because the square root of 16 is 4. So what are you doing to the sample size? You're multiplying it by 16, which means that if you want your margin of error to be 1/4 as large, you're going to need a sample, in this case, of 1600, which is why the answer is E. A lot of you chose D, and I can see why. You're thinking 1/4 is large, 400, but that's not exactly how it works, because you got to know that n is within the square root. Next class, I would like actually to finish reviewing a bunch of these questions, especially the red ones, and then we will continue with hypothesis testing, because there's a lot of things that we got to clarify when putting these things together. If you have not left a comment in the chat, please make sure that you do so. I can see you all right there so far, but I'm going to give it a moment for people to leave those comments in the chat, and I'll see you all next time. Thank you, too. See you guys. Bye-bye. See ya. Take a picture of that, and boom. Sweet. Okay, I'm going to sign off then. See you guys.